Hello, everyone. I'm Aljosha Demeulemeester. I am a senior graphics engineer and lead of the team working on graphics streaming tech within Unity. In this session, I'll be covering streaming virtual texturing and how to use it. So let's get started. I'll introduce Graphine, a middleware company. I'll talk about high resolution textures and what problems they create. Then we'll dive into what streaming virtual texturing is, when you best apply it or use it, and how to use it. What is next after that? What is on our roadmap? And then some final words to conclude this presentation. Graphine was a middleware company. You might have heard of it. We were already in business for 6-7 years before Unity acquired us. And Graphine was a university spin-off. So you can see the R&D team at Graphine here. You can see me in the center here with my white shirt. So the founding team, Bart, Charles, myself, the guys on the left, we were doing research at the Ghent University. Charles worked at Splash Damage at the game industry before doing his PhD. And out of that research and technology spun out Graphine. And we started to commercialize the technology as Granite SDK, which is a virtual texturing middleware. And that, at first was used for games, then virtual reality, then high-end games, and more and more in more and more applications. We were acquired in March in 2019, and now we are part of Unity Graphics R&D. So we are creating new features within the core Unity engine, and we integrated our virtual texturing middleware into the engine, and that is what we are talking about today. So we integrated Granite SDK. A large part was already rewritten on the editor side, so on the workflow side, but the runtime, the part that actually runs inside of the game that you distribute, is still more or less the same. And this was already used by a bunch of companies in a bunch of projects as well. So like high-end games, virtual reality, even augmented reality, and or for virtual production, visualization applications. So it's quite robust already. We've been working on it for quite some time. It's highly optimized as well. And this is definitely not new, but obviously it's very new to Unity and still in the industry, not used that much. So high resolution textures, I'm sure you've heard about textures, and if you want to add more textures or high resolution textures, you will run into issues. The main thing is memory. So high resolution textures use a lot of memory. And if you look at a PBR material with 4K textures, for example, that are BC compressed, then we see that we need roughly 50 megabytes of video memory to store them on the graphics card and to be able to actually render with them. So 4K PBR materials, that means that if you have 4K PBRs, textures per material, then we can have 21 unique materials for our 1 gigabyte texture budget, for example. That is not a lot, 1 gigabyte texture budget, and still we can use 21 of those, but in many cases you will need more. So if you have very high screen resolutions, you need more texture data because you need some detail to sample for every screen pixel. So if you want to use more unique materials in your environment, then you need more texture data or more texels. And if you want to import really high resolution assets that are super high res, then you need to be able to load more texels or texture data. But perhaps you don't have more memory. 1 gigabyte, you find graphics cards with 4 gigabytes, but not everybody has that. And definitely not all your target users. So a solution for that is texture streaming. So streaming virtual texturing is a texture streaming solution. It's a very specific, quite an advanced approach to texture streaming. And in virtual texturing, what we're going to do is we're going to take textures and we're going to take the UV space and we're going to divide it into very small tiles. So the entire map of the texture is divided into tiles that are 128 by 128 pixels normally. And these tiles are streamed individually, so you don't need to store entire textures in memory, you don't need to store entire maps. We can load only the parts of the maps that are actually visible or that need to be sampled in memory. So this way you can have higher resolution textures. If you have a 16K, for example, takes up a lot of memory, but if you only need to store the areas that are actually visible, you don't, in many cases, don't need that much memory. And so this is the foundation of the magic that is called streaming virtual texturing. So it's also sometimes called sparse textures, where again, this references to the fact that not the entire maps don't need to be entirely in memory, or virtual memory, for example, where to the programmer it looks like everything is in memory, but actually some parts are in physical memory and some are not. So if we apply virtual texturing and we divide textures into small tiles, then we need a different sampling approach, because we are storing these tiles into a tile cache, which in our implementation is a texture array. And then we need to find these tiles in that cache. So we are not using tiled resources or partially resident textures, which is kind of a hardware graphics API acceleration for the sampling. So we are using software VT, and so we are doing this in the shader. And basically we need to translate the UV, the virtual UV, into a location in our cache. So the bottom line here is that a VT sample is more expensive than a regular texture sample. So in your shader, a regular texture sample is just a sample. With a VT sample, we first need to sample the indirection texture. Then with the information we get, we do some calculations, and then finally we can sample the cache texture. So this is a bit more expensive, and this is the reason why it doesn't always make sense to use streaming virtual texturing on a material. In this system, we also need to figure out which of these tiles to load. So we call that residency management, figuring out which tiles to keep in memory. And this is done automatically. So it is based on what the main camera can see. And this, we bind an additional render target, and we render the tile IDs to that render target, and then we copy back every frame, we copy back that render target to the CPU to process which tiles were actually rendered, and this way we know perfectly which tiles are actually sampled. This always lags a bit behind, so that means we don't always have the right tile in GPU memory. But luckily, our indirection texture approach here allows us to actually sample from other tiles from lower resolution MIP. So if a tile from MIP 0 is not in memory, the indirection texture will point to a tile from MIP 1 or MIP 2 that overlaps that UV space. So automatically, without any delay or stalls, it just falls back to a lower resolution tile. And so after a couple of frames, or much later, depending on the speed of your hard drive, the tiles will finally, that were requested, will finally be in memory. So this is all done automatically. You don't need to do anything for that. But we also added an API to add requests for a frame. So you can actually do some prefetching. If you know some content will be necessary in memory, you can already request it. So that means you can request specific areas of textures, entire textures, and make sure it's already in memory before it actually becomes visible. And so the thing to remember is this is not direct management. You are not saying, you're not guaranteed that this will be in memory. So you ask the system to stream something, and depending on the amount of memory and other constraints, it will try to do that. And it might be able to do that within a certain time, but the data might never be loaded. So there are no guarantees. It's the best effort thing. And so, as I mentioned, so we render the tile IDs to a buffer. This gets copied back to the CPU. There we run some code, which we can call it a cache manager. This translates the requests into read requests that then reads pages from disk, which contain a bunch of tiles. And then these pages are read into a CPU cache. They could be compressed further. And then from these pages in the CPU cache, we actually copy the tiles to GPU memory into the tile cache texture that were visible and were required to render. And here you see a scene that is set up with VT, streaming VT. So these cubes, they each have 4K textures. And so once the camera is moving, parts of these textures are loaded automatically just in time. And you can see that only certain areas of these cubes are visible. Here you see the tiles, and the colors of the tile borders represent the bitmap where they are from. And so you can see as the camera speeds up, more tiles become visible every frame. And here I flush the cache, so we throw everything out of the cache if we toggle the debug view. And now after a little bit, the system can keep up with the camera speed. And so everything is just loaded in the background while playing the game. Here we have 80 of these materials, so that's roughly 4 gigabytes of compressed texture data, but we only have a cache of 600 megabytes. And that cache is even used only 20% for the current frame. That means the current frame needs 128 megabytes. So you could even set the cache lower, but we set it a little bit higher to keep some data around, even if it's not visible. And so streaming virtual texturing is different than bitmap streaming, obviously. So Unity has bitmap streaming, and both allow you to have large open worlds, but streaming virtual texturing shines for dense environments or really high resolution textures. So on the left side here we have a camera, and we use bitmap streaming, and let's say there's one 4K texture per cube here. So we have 4 cubes that are visible by the camera, and they are so close to the camera that these 4Ks need to be loaded in memory. If you then look at the right side, we see we have streaming virtual texturing. And we actually have 8 of these objects close to the camera, and so each has a 4K texture as well, but only small parts of these are visible. And some of these objects, although they are close to the camera, they aren't visible, or so none of the tiles need to be loaded. So the bottom line here is that we can have denser scenes where in this example we have many more objects close to the camera, and still we use less memory. Let's say we would upscale the textures to 8K, we would still require the same amount of memory, where in a bitmap streaming system you would use 4 times the amount of memory. Because in a streaming virtual texturing system, the cache size depends very little on actually the resolution of the textures and the content, and much more on the screen resolution, because in theory you only need 1 texel or a couple of texels per pixel. So obviously streaming virtual texturing is great, but there are cases where it's better not to use it. So it optimizes texture memory, but it comes as a cost. So it comes at the expense of performance. You need to spend some CPU cycles, GPU cycles for this system to run. So you shouldn't always enable it, but only in specific cases. It's not always clear. It's a bit a gray area. It's a bit specific sometimes, but there's just some general things to keep in mind, or when not to use it. Well, if you're not using high resolution textures, probably it doesn't make sense to use streaming VT. So textures, if you only have textures smaller than 1K or 1K perhaps, then it probably doesn't make sense. Also, if you do not have 1 to 3 milliseconds of frame budget, then you might not have the performance headroom. So you need to keep this in mind. And if your frame rate is already too low, then it might not be the memory optimization technique you need. Streaming virtual texturing also has a fixed memory cost, and if you cannot spend 250 megabytes of texture memory, it might not make sense. So it's a little bit, this one is more difficult. Sometimes it does, sometimes it doesn't. The point here I'm trying to make is that you do need to have some budget, like a minimum budget. And if you have only a few low resolution textures, you might probably use less memory without streaming VT than with streaming VT. So it doesn't apply everywhere. It doesn't optimize memory in every case. And then also, if only a very small subset of your materials actually qualifies for use with streaming VT, then and these are not always visible. So most of the time, no VT materials are visible. Then maybe it doesn't make sense to use streaming VT, because you're always paying the cost of having a VT on. So then you could bitmap streaming would probably be the next obvious choice. So which materials does it make sense on? Well, if it's always visible in material, then yeah, don't use streaming. If the texture are low res or an entire bitmap is always visible, then use bitmap streaming. And so the ideal candidates are high resolution textures that are not always visible and that are not completely visible. So for example, a 3D character facing the camera, you can't see the backside of it, so that can make sense. And preferably also only sample the texture once in your shader. So again, for a typical character, that makes sense. But let's say you have a noise texture that you sample many times in your shader, then the VT sampling cost might be measurable and be too expensive to use VT. So how to actually use streaming VT in your project? So first, you need to enable VT in your player settings. It is a project-wide setting. That means you cannot enable it or disable it per player, per target platform. And this is because in most cases you alter your content for use with VT. It's not always trivial if you have a game full of very large textures, very high resolution textures, to then port that to a platform that doesn't support VT and convert that to not using VT. So if you need to do that, you need to toggle off VT in your player settings and then potentially update your content. And so once you enable it, you will have caches created, you will have the system running, and then you need to convert your shaders to use VT. So instead of using regular texture samples, what you need to do is you'll add a virtual texturing property in shader graph, and then you will use a virtual texture sample to sample that property and connect that to the rest of your graph. So there's something weird going on here. You have multiple outputs, and I will come back to that later. But so basically, it behaves quite similar to a regular texture sample, but we need to know it's a streaming virtual texture sample. So you modify every shader, and then actually once you save the shader graph, and in the editor you look, you will see that it will run, everything will automatically be streamed. So the textures you assign to the material, to these VT virtual texture properties, will then automatically be streamed with streaming virtual texturing. Now, well, when you build the player, the texture data will be stored in a tiled, streamable fashion on disk in your build. And Also, a classic non-tiled version of that texture will be stored in that build because we can't know for sure that you are not going to use that on a regular texture sample. If you are using it only with VT properties, then on the texture importer you can toggle virtual texture only, and this tells us, hey, we don't need to store that regular non-tiled texture copy, and then we will make sure it is not stored in your build. Otherwise, you actually have twice the data, once tiled, once non-tiled. So as I mentioned, so it's a bit strange where you have multiple outputs on this virtual texture sample, and this is because we layer, or we use a concept called layering, where we every layer is actually a regular texture or behaves like a regular texture. And so if you have a PBR material with 3 textures, then the best thing to do is convert this to a virtual texture property with 3 layers. And the layering is just an internal virtual texturing optimization to make it faster. So as I mentioned, a VD sample is an indirection texture sample and a cache sample. Well, if you layer these different textures, then we only have 1 indirection texture sample and then 3 samples for each, 1 for each layer into the cache. Where if you would have independent virtual texture samples, we would for each independent sample have 1 indirection texture sample and 1 cache sample. So this layering is an optimization. So here you define the layers, and these are also exposed on the material, visible on the material as just like regular textures. And so you can find on the output the different layer slots and connect that to the rest of the graph. Now, if we don't connect all these layers, the texture to these different layers, then the current system will not cannot handle that. So you will see a error material. So you need to assign a texture to each layer. This is definitely something, a constraint we want to relax in the future, but right now all the layers need to be assigned. If something else is going wrong as well, and so the VT system for some reason cannot render, then you will see this error material. So now, cache management is obviously a very important thing with a streaming system. So how do you set your caches and how big do you set them? And so here there's something a bit unconventional where you actually have a cache per texture format, because a cache is nothing less than a texture array per texture format. A texture array has a format, so you need to configure the size for each texture array, and you can do that on the HERP asset. To there you can select the format and then set a size. This doesn't mean that that cache will be created per se. It will be created once a material uses a texture with that format, obviously a streaming VT material. And it's not always easy to determine the optimal size. So optimal is the smallest size where everything is still at the highest quality, the highest possible quality. And so a typical like full HD rendering, that might be in total 600 megabytes of video memory. So it's quite low for the ultra high quality settings, and then you could set it higher, but then the quality will remain the same, but it just can cache more. It perhaps has to stream less if it can keep more in the cache. So it's never bad if you have the memory to set them high. One thing to know is that these texture arrays, they take time to create and to destroy. So changing the size is not a fast operation. It's something you shouldn't do during regular gameplay, but only if you change specific quality settings. And so what we don't want to do is have cache trashing, where the cache is actually too small to hold the content that is rendered on screen. And for that, we have an automatic system that automatically sets a bitmap bias per cache or per texture format. And so once the cache is overused, the bias will go up, and that means that tiles from higher bitmaps will actually be requested. So if the bias is higher than 0, less tiles will be requested per frame, and so the texture quality will actually lower. This is applied to all VT sampling. And so that means that if you set the cache size lower than what the optimal size is, it will result in lower quality. And the system right now is set up to reserve at the minimum 1/3 of the cache for tiles that are not visible, or put in other words, like a maximum of 2/3 of the cache can be used for the current frame. If the current frame requires more tiles in the cache than 2/3, then the LOD bias will be set, and the quality will automatically be reduced. So it's not always easy to know what's going on. So for that, we have our virtual texture profiler chart, and there you can actually see what caches are created at what time and how much these caches are used. So if a cache is used 66%, and the mid bias is more than 0, that means that actually the cache is too small for the optimal quality. And so here we can see how many tiles that are visible in this frame. We can see the caches, the cache use, and this can guide our guide how we actually set the size. So ideally, you capture the cache demand during a play session, and the maximum of this per cache gives you the amount of memory you need for each cache to get the optimal quality. And then you can, based on the quality settings, maybe set it lower depending on how much memory you have available. So currently we only support HGRP. So right now we don't support the universal render pipeline. It only supports HGRP and the HGRP target platforms like PC, high-end consoles. And we still have a number of limitations that we want to remove. So there's still some work to do. And the most important thing, I think, for many game purposes is that we don't support asset bundles right now. So if a material is using VT, then you cannot store this material in an asset bundle, and the texture data will also not be stored in that asset bundle. So this is something we're working on right now, and also adding support for universal pipeline, render pipeline. We might not support very low-end platforms, so universal scales to many platforms. So we are sure that streaming VT can run on high-end mobile. It makes a lot of sense for virtual reality applications. So we are still thinking about what platforms we want to support, and definitely we want to hear from you what you need. But so probably our first focus is having asset bundle support, also a universal render pipeline support, and then we'll add more platforms depending on the need and depending on how we can optimize things to run on these low-end platforms. So we have a sample that you can already try. It's shared on our forum, and we will share some more links with you. And also, it would be amazing if you try it out and you tell us what you think and what problems you encounter, so we can make it better and add things that you need. So we have a survey, and you can go to our forum page as well to share what you discovered. So thanks for attending this Unite Now session on streaming virtual texturing. I hope you've learned a lot to help build your Unity skills and advance your projects, and feel free to provide us with feedback. Finally, be sure to check out our Unite Now page for other sessions that are sure to inform and inspire you.